Thank you to the organizers for inviting me. So I'm very pleased to be here. So I'm going to talk about the title here. The plan for the talk will be as follows. So first, I'm going to talk about a specific example of the general results. Okay, so that you have something in mind. Then I will talk about the general results that we proved with Vadim and Florent. And finally, I will discuss some possible questions for future research. Okay, so first, let's jump straight into the first example, which is the Gaussian beta ensemble. Okay, so this is the definition. So even before talking about the parameter beta, we're just going to talk about the Gaussian unitary ensemble. Okay, so this is a probability measure on n by n complex Hermitian matrices. So the space is Hn here. So the complex Hermitian matrices is a real dimensional vector space, right? So this is the Lebesgue measure on that vector space. And the density is proportional to this expression, exponential of minus trace of a squared, and let's say divided by 2, okay? And this Zn is just a normalization constant. So I have a random n by n complex Hermitian matrix. And because it's Hermitian, in particular, it has real eigenvalues. So the real eigenvalues will be x1, x2, up to xn, okay? And if you do the calculations, you find that this is the eigenvalue density. So the n eigenvalues are random eigenvalues, and the probability density in Rn that arises is given as follows. So this will be the van der Monde raised to the power of 2, product of weights, so product of exponential weights, and here is a normalization constant that I'm calling Zn, and then there's this upper index 2, and I will explain why there's this 2 later on, okay? But this is the distribution that I will be interested in first, okay? I will call this the GUE eigenvalue density or just the GUE density, okay? I want to see what happens with this as n goes to infinity. So the theorem here is very classical, is due to Wigner, is the following. So take your n random eigenvalues, okay, which are distributed according to this boxed distribution that I had. Consider the empirical measure, okay? So this will be a random probability measure, which has masses of 1 over n at the points xi. Okay, well, xi divided by square root of n, right? So that you see a limit shape. And I want to study this as n goes to infinity. And the theorem here tells me that the limit is the semicircle distribution, okay? So by the limit being the semicircle distribution, I mean that these equations are satisfied for any function which is continuous and bounded, okay? So here you have your random probability measure. So you take your integral, this will be a random number, and then you take the expectation, right? And the limit exists, and it's equal to this, the integral of f with respect to this semicircle distribution, okay? So very classical result, and if you prefer some visual version of the theorem, this is exactly the same theorem, but what I'm doing here is, okay, I'm considering n, which is very large. I put all the eigenvalues here. I draw the histogram in such a way that the area is equal to 1, right? So that means that there's more eigenvalues near 0. You can see here that the heights are larger, and there's less eigenvalues near 2, right? There could be some eigenvalue here, but it's very unlikely. And you can see that this limit shape appears, right? So this is exactly the graph of square root of 4 minus t squared, okay? So this is a very classical result. By the way, if you have any questions at some point, feel free to stop me, okay? Otherwise, I'll just continue. So, okay, very classical result. Now I will talk about some more general probability measure. It will be, I will call it eigenvalues of Gaussian beta ensemble. Okay, so there will be some parameter beta here, which will be bigger than or equal to 0 and real, right? So non-negative real number beta. And so the distribution that I will look at is the following. So it will be very similar to the one that I had before. The only difference here is that there will be a power of beta rather than a power of 2, right? And here even the weight is the same. And of course, the normalization has to change so that this is a probability measure, right? So this is a probability measure on R to the n. So it determines n real numbers, x1, x2, xn. Okay, and I want to see what happens also as n goes to infinity. So I will ask the same type of questions. Okay, so but first of all, maybe you want to ask why consider even this thing, right? It could be, you could just consider any kind of probability measure. Well, the reason is that certainly for beta is equal to 2, we have their interpretation, but turns out that for beta 1 and 4, you have also similar interpretation in terms of random matrices, which are orthogonal and symplectic respectively. Okay, so there's some random matrix interpretation for 1, 2, and 4. Okay, and also another reason is that I think that there will be people who are more familiar with this, but in physics, this is called a log gas system, right? And the parameter beta is the inverse temperature. Okay, so now you can see that. Okay, this talk I will talk about high temperature. So the parameter beta will converge to 0, right? That will mean that the temperature converges to infinity. But more on that a little bit later. Okay, so I will study this probability measure. So, okay, let's do the same type of thing. Consider the n random eigenvalues, okay? It will be distributed according to this distribution, which depends on beta. Take the empirical measures, okay, and see what happens as n goes to infinity. So if beta is fixed and positive, nothing changes. You have same type of result, and the limiting measure will be, again, the semicircle distribution. Okay, so everything remains the same. Now, something funny happens when beta is equal to 0, which I allowed before, right? So what happens when beta is equal to 0 is that there was this factor, which was the van der Molen raised to the power of beta, right? So if beta is equal to 0, this factor disappears, and the distribution will just be this product of weights, right? And in that case, the normalization constant is just this, right? So this tells me that the xi's are actually IID standard Gaussian random variables. Right? And so, of course, here, if you take these empirical measures, the limit will be different. It will not be the semicircle, it will just be the Gaussian distribution, okay? So there's kind of a jump. When beta is equal to 0, I have the limit, which is the Gaussian. When beta is positive, I have the semicircle distribution, right? So for any positive, you have the semicircle distribution. So next theorem, which is one of our results, is a bridge between these two. So beta will go to 0 at the same time as n goes to infinity. So that's a theorem. And also Dewey and Shirai in 2015, they have the same result that's stated here. That's the following. Take the n eigenvalues x1 through xn, okay? They're distributed with respect to this measure, which depends on beta. Look at the empirical measures. In this case, the xi's need to be divided by n, okay? And look at this regime, which I call the high temperature regime, right? So recall beta is the inverse temperature. So beta has to go to 0. And I do it in such a way that n times beta converges to a constant. So n times beta divided by 2 converges to gamma, okay, which is positive. So theorem tells me that these empirical measures converge weakly in probability in the same way that I had before to certain probability measure, which is mu gamma. So it depends only on gamma, okay? And this mu gamma can be completely described, but for now, this is the theorem, just that there exists some limit shape, okay, essentially. So of course, okay, this is good. This is a good theorem, but it's not complete because I want to describe this probability measure, okay? So this has appeared before and there's a density for it, but we will give a new formula for describing this probability measure. We will describe this probability measure by the moments. Okay, so that will be the second part of the theorem, describing this limiting measure in terms of the moments. So I will do that, but for that I will need some combinatorics. Okay, so this is the fun part. So I will need perfect matchings. Okay, so I need a set of 2n elements so that there is some perfect matching. Okay, perfect matching is just you pair these 2n elements into n pairs. Okay, very simple. So the pairs I will call blocks b1, b2, bn. Okay, so they're all disjoint and the union is the set of the first 2n elements. So for example, here in this picture, you have the perfect matching 1, 6, right? 2, 7, 3, 8, and 4, 5. Okay, so that's a perfect matching of set with 8 elements. So then you do the following. So to each perfect matching, I will define a statistic called the root statistic. It will be the following. So first you need to draw the arc diagram of the perfect matching, okay? So what is that? You label the blocks in such a way that the first block is the one that has the smallest element. 1 is always the smallest element, so this will be the block B1. Next block, the one that has the next smallest element, so 2, right? Next one, the next smallest element, this is the block 3. And then the next smallest element is 4, so this will be B4. So B1, B2, B3, B4, okay? Then you draw these arcs, right? So these arcs is just some small house, right? But you draw it in such a way that the roof of B1 is the tallest, right? So 1.6 is the tallest building, right? Then 2.7 is the next tallest, 3.8 is the next tallest, and 4.5 is the smallest, right? So that's the arc diagram of the perfect matching. And then the roof of the perfect matching, roof of pi, has been the number of roofs with no intersection, okay? So take a look at this. So 2.7 has an intersection, right? That the roof has an intersection, and the roof of 3.8 has 2 intersections, okay? So those do not count. But the roof of 1.6 and the roof of 4.5 do not have intersections. So in this case, the roof of pi is equal to 2. Okay, and for each perfect matching, you do this procedure, you obtain some statistic. And the theorem is that this is new formula for determining the limiting measure, is that this limiting measure is uniquely determined by the moments. And the moments are the following. The kth moment is a sum over perfect matchings of a set with k elements. And you add these numbers, gamma plus 1 raised to, and then the roof of pi, right? The roof of your perfect matching, okay? So this gives you a nice, neat formula for the moments of the limiting measure. Gamma is beta times n divided by 2 converges to gamma, yes. Yes, then 4 would be the next smallest element. Yes, yes. Okay. Okay. So that's our theorem. Just want to make, so before I go to what the general results are, okay, so this was an example. I want to make some comments about this formula. I want to say what happens when gamma is 0 and when gamma is infinity, okay? Why is that? That's because gamma is equal to 0, as I just said, the gamma will be beta times n divided by 2, right? So if gamma is 0, that means that beta is 0, right? So we should see the Gaussian moments here. And if gamma is infinity, that means that beta is fixed. So we should see the moments of the semicircle distribution here. And that's indeed the case, right? So, well, okay, so first obvious comment is that if k is odd, there's no perfect matching. So the odd moments are equal to 0, okay? The even moments are non-trivial, always. And if gamma is equal to 0, for example, each term here will be just 1, right? So we will have the number of perfect matchings of a set with 2n elements. You can count those. It's given by this product, 2n minus 1, 2n minus 3, and so on. And you know that these are the moments of the Gaussian distribution, right? This is the 2nth moment of the Gaussian distribution. Now, if gamma goes to infinity, okay, you need to do something else, right? You need to divide first by gamma to the n, and then you can send gamma to infinity to the right-hand side, right? The only terms that will survive are the ones for which the roof statistic is the maximum possible value, right? If the roof statistic is the maximum possible value, that tells me that there's no intersections. So each roof doesn't intersect anything. So that corresponds to non-crossing perfect matchings, okay? So that tells me that the only terms that survive in the limit as gamma goes to infinity are the ones corresponding to non-crossing perfect matchings, and those are given by the Catalan numbers, okay? Which are the moments of the semicircle distribution as well. So this formula is nice, and it degenerates to classical results when gamma is 0 and gamma is infinity. So, okay. Now we want to go to the next part of the talk. I will want to explain, you know, not in a lot of detail, but just to give you some idea what the general theorems are, and to give you some idea of the kind of mathematics that are behind the proofs. So general theorems and proof ideas. So, okay, so I will describe 2 main theorems of our work with Vadim and Florent. So the first main theorem, you can think about it as a generalization of Levy's continuity theorem. Okay, so let me remind you what Levy's continuity theorem is. You have sequence of probability measures, mu n, and another probability measure mu, okay? So for each probability measure, you can associate this Fourier transform, okay, which is just a function on, so let's say that the probability measures are on R to the D, okay? So D Euclidean space. Then the Fourier transform is a function on R to the D, and it's given by this integral, right? So you integrate this exponential with respect to one set of variables that I'm calling A here, okay? So let's say that phi n is the Fourier transform of mu n, and phi is the Fourier transform of mu, okay? So Levy's continuity theorem tells me that weak convergence of probability measures is equivalent to pointwise convergence of Fourier transforms, okay? And there's nothing too mysterious about this statement because, okay, for example, you know, at least when the measures are compactly supported, this can be proved quite easily because weak convergence of measures of compact support is equivalent to convergence of moments, right? And you can obtain the moments from the Fourier transform by this simple procedure here. So you take a few derivatives with respect to the xi's, right? And then you set the xi's equal to 0 after you take the derivatives, right? So that should give you this moment here. So you take partial with respect to x1, partial with respect to xd, right? You set the variables equal to 0, that gives me this moment here, okay? So, okay, what kind of generalization are we talking about then? So in our work, okay, so first of all, I want to say that just to draw attention to the similarity with Levy's continuity theorem is that our theorem can be stated in some way like this. So law of large numbers for the empirical measures of these sequences is equivalent to some convergence of the Taylor coefficients of logarithm of something that I will call informally beta Fourier transform. Okay, so I will define some notion of Fourier transform, which depends on parameter beta. And theorem here will be that law of large numbers is equivalent to, you know, some kind of convergence of the beta Fourier transforms. Okay, so it's essentially a Levy's continuity theorem. Okay, so what is the beta Fourier transform that I will consider? Actually, the more proper name is the Dunkel transform. Okay, so this is a well-known object and arises in other areas of mathematics. And essentially, it has the same definition as before, but the kernel, recall that before it was e to the I ax. Now it will be this thing, which is something called a multivariate Bessel function, okay? So this is some kind of a special function for which the definition is here, right? So it's the unique function satisfying these three conditions. So first of all, it depends on two n tuples, a and x. I'm putting here the vectors, vector notation. It depends on the parameter beta too. In general, beta could be complex, but for our probabilistic applications, beta will be non-negative real number, right? And the definition is the following. So the first two conditions are kind of not too bad. So this function has to be symmetric on the variables xi. Need to satisfy certain normalization. So the xi's, when they are equal to 0, then the Bessel function becomes equal to 1. The third condition is the more involved one, and it tells me that the multivariate Bessel functions are eigenfunctions of the Dunkel operators, pk, for each k. Okay, so there's this thing called the Dunkel operators. They are differential symmetric operators on the variables xi. Okay, I will not tell you what they are, but they are some kind of some hierarchy of operators which determines this type of a special function. Okay, so I will not tell you what the Dunkel operators are or explicit formulas for this multivariate Bessel function, but I want you to have some rough idea of what they are, right? Because they appear in the beta Fourier transform, the Dunkel transform. So okay, so I will give you something to think about. So when beta is equal to 0, I can tell you what the Dunkel operators are. When beta is equal to 0, the Dunkel operators are just these things. So partial with respect to x1 raised to the power of k plus ... plus partial with respect to xn raised to the power of k. Okay, and then you can check that the multivariate Bessel function is given by this formula here. Right, you can check that it's symmetric with respect to the xi's. It is satisfied the right normalization. That's why I have the 1 over n factorial here. And this is an eigenfunction of these operators too, right? With the right eigenvalues. Okay, so that's the the simplest case, right? So you can think of this multivariate Bessel function as a deformation of the exponential, which happens when beta is equal to 0. Okay, so another that's more interesting is what happens when beta is equal to 2. So there's this thing called Harish-Chandra Ensemble integral, or also spherical integral, okay, which is the following. So it's an integral over the unitary group with respect to the Haar measure, okay, of the following expression: e to the trace u dA is the n by n matrix, diagonal matrix with entries AIs, okay? And dx is defined similarly, it's a diagonal matrix, right? U here is the unitary matrix, the random unitary matrix, and you integrate this, okay? So that's your spherical integral. So this is exactly my multivariate Bessel function when beta is equal to 2, okay? And when beta is equal to 1 and 4, as we have seen in the previous example, also turns out that there is some nice interpretations of the multivariate Bessel functions as spherical integrals over the orthogonal and symplectic groups, okay? So that's another thing. And if you're a symmetric functions lover, as myself, you'll be happy to find out that multivariate Bessel functions are also limits of McDonald polynomials, right? So there are some kind of continuous limit of these two-parameter symmetric functions. Okay. So let's continue back with what the first theorem is, right? I gave you an abbreviated version. I will give you now the actual version. So recall that we needed this beta Fourier transform. So we need to do the same type of thing, right? So recall that before I had this kernel and I used this type of operators. So now I will have this kernel, the multivariate Bessel function, and I will need to use this Dunkel operator, right? And the kind of equation that I have is the following. So to your beta Fourier transform, you hit with a bunch of Dunkel operators and then set the variables xi equal to 0, right? That should give me the moments of the measures in question, of the mu-n's. And that's exactly what I have. These are the moments of the empirical measure of the AIs, okay? So this equation is really nice because, first of all, it gives me an idea of how to proceed, right? So in, just following the proof of Levy's continuity theorem in a sense. So I will have the same thing here, right? And it's nice because this is the same equations as before. The only difference is that instead of gn to the gnb, I'm putting e to the log of gnb. Okay, but they're the same equations. And so on the left side, you have information about the analytic functions, about these beta Fourier transforms. And on the right-hand side, I have probabilistic information about mu-n. Okay, so this equation ties both worlds. Okay, so if I want to prove law of large numbers, so I want to look at the right-hand side and see when that has limits, I might as well look at the left-hand side and see when that has limits. Okay, so that's exactly our theorem. So our first main theorem, right? The first main theorem is that law of large numbers for sequences of particles is equivalent to the existence of limits of Taylor coefficients of this logarithm of the beta Fourier transform, okay? So more precisely, the following two are equivalent. So here, this is what I'm calling law of large numbers, okay? So what's here is the moments of the empirical measure of the AIs, and these are some products of some variables m's, which are finite, right? So the m's will be the moments of the limiting measure, right? So those are the formulas that I gave you for the particular example, right? But this law of large numbers is equivalent to some convergence of the Taylor coefficients of this logarithm of beta Fourier transform, okay? So these are the precise statement. So these limits of, you take partial with respect to x1, you take L partials, that gives me KL, okay? And if you take any mixed derivatives of the logarithm of this beta Fourier transform, you should get 0, right? Recall that we're talking about the high temperature limits. So n goes to infinity and beta goes to 0, okay? So this is our first main theorem, some type of sophisticated Levy's continuity theorem, okay? But this is very useful because in particular, it helps us prove theorems for some beta ensemble type particle systems, right? So like the one that I gave before. So how does it help us? Well, for example, for the eigenvalues of Gaussian beta ensemble, you can calculate precisely what the Dunkel transform is, or what I'm calling the beta Fourier transform, just to be a little bit informal. And it's given by this formula here, right? So you can actually calculate it. It gives me this very simple formula. So that reveals that this Gaussian beta ensemble is not any type of measure, right? It's very integrable, right? So because I can calculate this beta Fourier transform, it's given by this formula. So if you go back, you can check that it satisfies these conditions precisely, right? Because if you take, say, partial with respect to x1, then partial with respect to x2 of the logarithm, you get 0, right? If you take two partials of the logarithm, you get some constant, so k2 is equal to 1. And if you take any other number of partials with respect to x1, you get 0. So kappa 1, kappa 3, kappa 4, they're all equal to 0, okay? So our theorem, the first theorem tells me that therefore there is a law of large numbers, right? So that was the first part of the theorem at the beginning of the talk. But of course, that wasn't enough for us, right? We needed to say what were the moments, so what were the MKs, right? So I need some formula that relates the MKs, the moments, to the kappas. In this case, the kappas are very simple, but the moments may be too difficult. Okay, so we need some more, right? So that's our second main theorem. It's a relation between the MKs and the KLs in our first theorem, right? So if you do the calculation, so you need to work with the Dunkel operators, right? So you need to look at them. You need to analyze the combinatorics. And so you can do the first few calculations. I have the first few calculations here. I didn't write completely what M4 is, but roughly this is it, right? But because the kappas in the first example are almost always equal to 0, you can already see some things, right? So for example, M1, M3 is equal to 0. M2 is equal to gamma plus 1. M4 is equal to only kappa 2 raised to the power of 2 will give me something because the rest of terms will be equal to 0, right? So I have gamma plus 1 times 2 gamma plus 3, right? So second main theorem is a general formula for these things, right? So I have MK is equal to some function of the kappas and gamma, but what is the precise formula? So that's the one formula that I will describe right now. Okay, so more combinatorics. Okay, so this is my favorite part. So now I will deal with things that are more general than perfect matchings. So I will have a set with k elements, 1, 2, 3 up to k. K doesn't need to be even in this case. And I will have set partitions rather than perfect matching. So set partition is that you just break this set into blocks that are disjoint. So I'm calling them B1, B2, BM, okay? So for example, here you have 1, 3, 5, and 7, 2, 4, and 8, and 6. 6 is a singleton, right? It only has one element. That's okay. So then I define this, I need to define a weight of this set partition as well, right? Before I had gamma plus 1 raised to the roof. Now I will have this more complicated expression here. So what is this complicated expression? So there is some cardinality of BI. That's just the number of elements of the block BI. That's simple. What is PI? So you will have one PI for each block BI, okay? So the way to do that is to draw the arc diagram again, right? So it's essentially the same procedure as before. I order the blocks according to the smallest element that they have. So for example, this block has element 1, so that will be B1. Next block will be 2, 4, 8 because the smallest element is 2, right? And the next block will be 6, right? Already it has the next smallest element. So then I draw the arc diagram. That means that I draw these buildings. Now they will have many, or these kind of like chairs with a lot of legs, right? The tallest chair will be the one corresponding to B1, so 1, 3, 5, and 7. Second tallest chair will be corresponding to B2, and so on, okay? So PI will be the number of roofs of the block BI with some intersection, okay? So, okay, so I maybe will write here. Okay, I think it's okay. Hopefully you see this. So this is an arc in general. In this case, it has 5 legs and it has 4 roofs. So one roof is a space between chairs, or between legs, I'm sorry. Okay. So for example, the first block, 1, 3, 5, and 7 has 3 roofs, right? The next 2, 4, and 8 has 2 roofs, and 6 has 0 roofs, okay? Now, P1 will be what? The number of roofs with some intersections. So this has no intersections, right? So P1 should be 0. P2, okay, so there is 2 roofs, and each of them has at least 1 intersection. So P2 has to be 2. P3, okay, there's no roof, so P3 is 0. Okay, then you compute this weight. Okay, so I did it already. It's 2 times gamma plus 1, gamma plus 2, gamma plus 3. Okay, so that's some weight. And theorem, the second main theorem is that the kth moment, mk, is equal to this formula. So sum over set partitions of the weight, and then you take product of kappas. Kappa and then the size of B, okay? So in particular, this degenerates to these other formulas that I have. 1 second, right? Small cases. This is the general formula, okay? And if kappa 2 is equal to 1 and all the rest of kappas are 0, this formula degenerates to the formula that I gave initially for perfect matchings, right? Makes sense because if only kappa 2 is non-zero, then the only set partitions that count are the ones that have blocks of size 2 exclusively, okay? Okay, so that's good. I think maybe I'm rushing, but I think I'll have plenty of time to discuss some future questions, okay? So I want to mention a few directions, some of which I'm thinking right now, some of which not so much. So first one is the relation between the MKs and kappa Ls, okay? So those may have seemed familiar to you already. And the reason for that is because if gamma is equal to 0, the relations that I had here, right? Remember the first 4 relations that I wrote? They're the same as the relations between moments and cumulants of a probability measure, right? So if gamma is equal to 0, the limiting measure had moments MKs and had cumulants kappa Ls, okay? So if gamma is equal to infinity, you need to make a small modification, but those relations are also the same as the relation between moments and free cumulants. Okay, so for each measure, you can associate some other sequence of quantities called free cumulants, some of the main quantities in the theory of free probability, right? And it turns out that there is some nice formulas between them. And the formulas we have also generalize those. Those are the special case when gamma is equal to infinity, right? So these kappa Ls, I will denote the gamma semi-free cumulants, okay? So I will call them gamma semi-free cumulants because they interpolate between classical and free cumulants. Now, one problem that I want to mention here is, okay, so this is a little bit extreme, but you know, study the gamma semi-free probability, okay? So what do I mean by that? So I will state a precise conjecture here. So this is a conjecture, okay? So I would be happy if somebody can answer this question. So take 2 probability measures, let's say of compact support, mu and nu, okay? So they are compactly supported, that means that all the moments are finite, okay? So then you can use the formulas that I had to compute the semi-free cumulants of these probability measures. So they have all the semi-free cumulants, kappa L, for any L bigger than or equal to 1. So for mu and nu, okay? Now, conjecture is there exists a unique probability measure, also compactly supported, such that the Lth semi-free cumulant of that measure is equal to the sum of the semi-free cumulants of mu and I think I made a mistake here. It should be nu, right? Okay. So, and by comparison with the case when gamma is equal to 0 and infinity, such a measure should be called gamma semi-free convolution, right? So this would be an operation that interpolates between classical convolution, right? So if you have two random variables, you add them together. If you look at the distributions, this operation is exactly the convolution, right? So then there is some operation in free probability called free convolution. And claim is that this operation is also valid at the level of probability measure. So, you know, there exists some probability measure for which these equations are true, okay? So this is one question that one conjecture that I will leave here. Okay, and another possible direction of research is just, even without having this conjecture, I think it would be interesting to study other questions. For example, you know, I'm putting an example here. So classify the infinitely divisible laws with respect to this operation of semi-free convolution, assuming that it's an actual operation between probability measures, okay? Or, you know, you have many possible questions. Just you look at free probability theory textbook and try to see which ones have analogs, right? And which ones produce new phenomena. So for example, one of the results that we have is some connection with random matrix theory and law of large numbers, okay? So I will state this statement because I think I have time. So, so this will be, actually, this was the application which motivated us to pursue this direction of research. So it's the following. So take sequence of n tuples AIs and another sequence of n tuples BAs, okay? Then take a random matrix A, which has these fixed eigenvalues, and take another random matrix B, which has these fixed eigenvalues. So A and B, so I'm calling them AN and BN here, are matrices with fixed eigenvalues, but random eigenvectors, okay? So then you take the sum of these two random matrices and you look at the eigenvalues of the sum, okay? So the eigenvalues will not be deterministic anymore, they will be random, okay? So and then you can ask what happens when n goes to infinity. So a theorem of Voiculescu in 92, I should have written it here, tells me that if the A's converge, if the empirical measures of the A converge to mu, and the empirical measures of the B's converge to nu, then the eigenvalues of the sum, the CIs, I'm calling them here, converge to the free convolution of mu and nu. Okay, so the very beautiful result. So we have a high temperature analog of that result. Okay, so we define some kind of beta sum of random matrices. Okay, so if you look at the eigenvalues of that sum, and you look at the high temperature limit again, so if n goes to infinity and beta goes to 0, in such a way that n times beta is a constant, then the eigenvalues converge weakly to the semi-free convolution, okay? Mu, and then the semi-free convolution with nu, okay? So here, in stating this theorem, I'm assuming the conjecture to be true, but we actually stated it in terms of generalized functions or distributions in order to make this theorem actually precise, okay? But it will be more beautiful, in my opinion, if somebody proves the conjecture, so please let me know. And you can also ask more questions, what questions in free probability are true in this new setting that we have in our paper. So, okay, this will be the last thing that I talk about is some discrete analogs, okay? So this is current work. So work in progress with Maciek Doliega and Alexander Moll, okay? So on discrete ensembles, okay? So let me tell you what happens here. So let's begin with something that you might be familiar with, for example, from the last talk already. So begin with this equation here, okay? So this you have seen in representation theory of the symmetric group, right? In your class of representation theory. Sum of dimension of lambda square is equal to n factorial, the size of the symmetric group, okay? So what is this dimension of lambda? Dimension of lambda is the dimension of an irreducible representation of the symmetric group, okay? And lambda varies over partitions of size n, okay? So this is classical theorem called the Bernstein identity. And what I will do is divide both sides of this equation by n factorial. So on the left side, I have a sum of numbers, and on the right side, I will have just one. Okay, so that gives me a probability measure, which will be the Plancherel measure. So Plancherel measure is a probability measure on partitions of size n, which is given by this formula, dimension squared divided by n factorial. But if I use this hook length formula, okay, classical result also in representation theory of symmetric group, that tells me that the dimension of lambda is n factorial divided by the product of hooks. Then I have that the Plancherel measure is given by this formula here, n factorial divided by product of hooks square. Okay. So, okay, so what happens here? I have some partitions. I want to see what happens as n goes to infinity. Of course, I have to first explain how to view these these probability measures. So I will represent my partitions in the following way. So for example, this is the partition 5, 4, 1. So this is a partition of 10, right? 5 plus 4 plus 1. I will represent it by Young diagram. Okay, so it's just a sequence of boxes. 5 boxes on the first row, 4 on the second, 1 on the third. Okay. So then what you do is that you will rotate this partition by 135 degrees, right? So here you will have another partition. Okay, this is a larger partition, right? So this partition, which is here, you rotate 135 degrees, you have a partition in this wedge. And of course, this will be a large partition because, you know, as you can see, there's many boxes here, okay? Then you will rescale the partition by 1 over square root of n in both directions, just so that the area of the partition is equal to 1, right? So you have a small boxes of area 1 over n, and you have n boxes, so the area should be equal to 1. Okay, so as you can see here, okay, there is a limit shape phenomenon occurring. And that's exactly some theorem of Vershik-Kerov and Logan-Shep, 1977, so it's a long time ago, that tells me that if you look at your random partition, lambda, and then you normalize it and you draw it in this way, okay, I don't want to make anything too precise, but you will see a limit shape, essentially, right? And that limit shape is this, given by this formula here, right? So it is compactly supported. So outside of a small interval, it will just be the trivial, right? The wedge, square root of absolute value of u. But inside -2 to 2, you have this non-trivial formula, okay? So this is called the Vershik-Kerov Logan-Shep limit shape, okay? How much time do I have left? 5? Okay, perfect. So, okay, so that's a very classical result. And now, of course, as you can see from previous examples, I want to look at the high temperature limit shape, okay? So what do we mean by high temperature limit shape? So you need to have a parameter beta. So this will be my definition. So there will be a 1 parameter degeneration of the Plancherel measure, okay? That I will call alpha Jack-Plancherel measure. Jack because it's related to Jack polynomials, but it's given by this simple formula right here. So it will be alpha to the n factorial, right? Divided by, and then there will be product of hooks, alpha deformation of hooks to be more precise, right? So you have one possible alpha deformation, another possible alpha deformation, okay? And this gives me a probability measure on partitions of size n, capital N, okay? Now, why do I consider this particular degeneration, right? You could degenerate in many different ways. Well, and it has been done actually, but you know, you have to believe in something. So I believe that this is some kind of beta ensemble type measure. So this is, for many integrable reasons, some kind of beta, well, exactly what I'm saying here, beta ensemble type measure, right? So in the parameter beta, coming from random matrix theory, and the parameter alpha coming from symmetric function theory are related to each other by this equation. So beta is equal to 2 divided by alpha, right? So alpha is actually proportional to the temperature here. Recall that beta was the inverse temperature. So if I want to look at high temperature, I want alpha going to infinity rather than to 0, okay? So, okay, I need to do something more too. So instead of drawing the partitions in the usual way, I will need to draw an isotropic partition. So this is a terminology introduced by Sergei Kirov, which tells me that instead of having boxes of size 1 by 1, I will have boxes of size square root of alpha times 1 over square root of alpha. So the boxes still have area 1, okay? But they will be, you know, modified a little bit. So they will be either long or, you know, or thick. So for example, here you have your partition 4, 3, 1. And if alpha is equal to 1 over 4, square root of alpha is 1 over 2. So this will be my alpha anisotropic partition. Okay, you just change the form of the squares drawing the partition. So okay, you draw your anisotropic partition. You consider a large partition, and you still, in this case, you just rotate it 45 degrees, right? In the way that's here. You rotate it 45 degrees so that the partition is on this wedge, and see what happens as n goes to infinity, right? So this theorem here, due to Maciek, Doliega, and Piotr Sniady, 2019, is that, okay, you look at this high temperature regime, so n goes to infinity, alpha goes to infinity as well, n divided by alpha goes to g. G is some number which is fixed between 0 and infinity, okay? And just putting g just so that you don't confuse it with gamma. Then there exists a limit shape, okay? So there is a limit shape. That means that if you draw the partitions, they will approximate certain function which depends only on g. I'm calling here omega g, okay? And this function, you know, in particular, because it's the limit shape of some partitions, when u is large, it will just be absolute value of u, okay? So that's very nice, and then this is a nice result, but compared to other previous results, it's a little bit unsatisfactory, just like it's stated here. That's because I'm not telling you what omega is, right? So I'm not telling you what omega is, right? So, and what are the formulas for the moments, right? So we had some nice combinatorial objects. And so that's exactly work in progress with Maciek, Doliega, and Alex Moll. And that gives me exactly, you know, a complete description of omega. So it's a little bit not extremely direct, and it involves something that was mentioned in the previous talk as well. So there's something I don't want to talk too much about what this is, but it's called Markov prime correspondence, that to each limit shape omega, it associates a probability measure nu omega. Okay, so there's some kind of procedure, and this is called the Kerrov's transition measure of the limit shape, okay? So, and that's our theorem. So this will be our theorem. And this will be, you know, a special case of our theorem, which tells me that the limit shape is uniquely determined by the moments of the transition measure, okay? And these are the moments of the transition measure. So the nth moment of the transition measure is given by this sum over some combinatorial objects of this expression here, which depends only on g. Right, so it's a sum over Motzkin path. Again, a picture is better than 1,000 words. And then there's some statistics on the Motzkin paths that appear here, right? So in particular, the exponent of g is related to the number of horizontal steps in the Motzkin path. And the power appearing in on top of g corresponds to the horizontal steps at height j, okay, at height j. So okay, so then that will be appearing in future work, right? So that's it. Thank you for your attention.
So your model of beta dependent random matrices has an analogy in quantum mechanics called Caligera-Sutherland model. And my question is, if you consider kind of higher order correlation function, if it's possible to, for example, to look at the density. You just calculated mean density of the particles. Is it any chance to get density correlation functions? Because it can be an interesting question when in your limit when beta goes to 0.
Density.
The correlation function of different eigenvalues, if you wish.
I see.
Not just their mean density, but the correlation of this.
Correlation, okay. Yes, I don't know about this, but yeah, it's a good question. I mean, there are some other things that we could look at also, such as central limit theorem, for example. But yeah, I understand your question, but yeah, we haven't seen that aspect, I think. Yeah. So in this case, we will not see those because beta goes to 0. But yeah, I think we would need some other formulas. I don't know.
So I was just wondering, like, how hard is it to generalize, especially the first part of your talk, to non-Gaussian ensemble?
To what?
Non-Gaussian.
To non-Gaussian. Well, we have other ensembles, for example, the Laguerre beta ensemble. We have results for those too. The thing that did allow us to obtain that particular result on the first part of the talk was that we were able to calculate the Dunkel transform, the beta Fourier transform of this measure. So, you know, it's some kind of integrable system. So it's not any system. But of course, we have this general theorem too, which tells me that if there is some law of large numbers, there has to be some limits of the Fourier transforms. But in order to actually show what the answer is, you need some integrability. So besides the Gaussian, again, you know, there is Laguerre, maybe Jacobi. We haven't taken a look at that, and we have a bunch of examples. But in general, you know, for example, general potential or something, yeah, that could be nice to look at. I don't know.
So you said that you talk about the multivariate Bessel functions, and you said that they are special limits of McDonald polynomials. Can you be more precise?
Yeah, so the McDonald polynomials depend on partitions of size n and on n variables, right? So the partition is lambda1, lambda2, lambda n, and the variables are x1, x2, xn. So the partition will become one of the sets of variables, right? So the multivariate Bessel function depends on two sets of parameters, a's and x. Right, so it depends on a's and x. So a's come from the partition, lambda1, lambda2, lambda n. So you need to take some kind of continuous limit of that. And the x's are just the x's from the McDonald polynomials. Well, you need to do something like x is equal to e to the epsilon yi, something like that. And then, you know, you will have y's here, something like that. Oh, that's a good point. T is equal to q to the beta over 2, and q goes to 1.
Yeah, I had a question actually. I mean, in the case of the Gaussian beta ensemble.
On what?
In the case of the Gaussian beta ensemble, so the first example that you discussed, in fact, the limiting distribution, which you call mu gamma, it can be explicitly computed, right? I mean, this was computed by Allais, Guionnet, and Rouchot.
Yes, exactly.
I think in terms of some parabolic cylinder function, so you have a fairly explicit expression. I was wondering whether it's possible to connect your formula for the moments and the formula for the density.
Yes, that's a good question. We haven't really tried. There was one of our co-authors, Florent, he has another paper where he describes another formula for the moments, and I think he talks a little bit about this, but yes, we haven't even tried. I mean, in theory, they are the same objects, right? So we should go from one to the other and from the other back. And yeah, I think that this is something to verify just directly, but we haven't done it.
Yeah, also in their paper, they made a kind of conjecture that it's possible, at least in some range, to extend their results to negative values of gamma.
Negative values of gamma, okay. Interesting.
Is it something that you can think of here?
We haven't looked at that, but you know, since our techniques are algebraic, maybe that would be possible. Yeah, I have to check. I need to read. I didn't know about this. Then I can mention that there have been a set of authors that they discussed finite free convolution, and they have some negative parameter there. Yeah, so I'm not sure if this is related or not, but yeah, it's need to tie a few dots.
It's rather a comment, and actually it's not even totally related. Could you please go to the last slide?
Yes.
Well, just because it was a nice picture. Okay, if you consider the top the diagram on the top, 20 years ago, maybe we were interested with Andrea Capelli in computing the number of pairing according to the number of crossings. Okay, so it's quite a related situation. We are considering the number of non-crossing. And actually we had some expansion and we studied the asymptotics of the distribution. And it was, we counted this diagram accounting to some Q elevated to the number of crossing. And it appears that we had interpolation between semicircle and Gaussian. And these measures are actually interpolated by the Q Hermite polynomials. Okay, so this allowed us to work out several explicit formulas. I think that your counting is slightly different, but maybe there is some relation or something to investigate further in this direction.
Yeah, so actually I've given this talk a few times, as has Vadim, and you know, we have received like a lot of comments about this particular statistic, and we figure out after we posted the first version that the moments that we have are the moments of associated Hermite polynomials. Okay, so they are the moments of associated Hermite polynomials. But yeah, so our only thing is that, of course, they didn't know about this random matrix stuff, right? But yeah, so it is related. I'm not sure how the relation between this associated Hermite and the ones that you have are. Maybe, probably they're the same. So, but it's interesting that it appears. Okay.